Welcome to our final transformation video. We've all been here before, downloaded your favorite picture, wanted to keep it looking the same, but maybe shrink it a little bit, or perhaps got the perfect picture you wanted, needed to enlarge it a little bit. But notice how we just click on the corner and we drag and it enlarges it or minimizes it, proportionally speaking. The process of doing that with the picture is just clicking on the corner. I'm not sure what the technical Microsoft Word name for that would be, but the math term for what you're doing there, reducing and enlarging but keeping things proportional, is called dilations, and that's our final transformation that we'll do. And to be honest, probably the easiest of the four transformations that we'll have to do. Here's what a dilation is. First of all, it's the reduction or enlargement of an original object. It has a scale factor. As you can see right here, it's known as K. And when you compare the image to the pre-image, so what's the final product compared to the original product or the original size, that gives you your scale factor. Any value that's above 1, meaning the image ends up being larger than the original pre-image, implies that you've had an enlargement. Any value less than 1 indicates that the new image is less than the pre-image, so K less than 1 implies a reduction. Over here you'll see that I have this kite A, B, C, D, which is the original object. Now we're looking at A prime, B prime, C prime, D prime. We're looking at a miniature version here. This would be a reduction, and you can see just by the fact that we were at -4, 0, and now we're at -1, 0 here, that we have had a reduction, and to be exact, this would be by 1/4, but we'll talk a little bit on the next two slides how to get that, but this here has been a reduction. One thing I will also add is that all of our dilations will occur about the origin 0, 0. So let's take a look at an example here. What would we do if we had a dilation of K equal to 2? Well, here are our original points of the triangle ABC. A, -2, 3, B, 1, 1, C, 5, 4. It really is going to be as user-friendly as you might think. We want to have a larger object. Luckily, it's around the origin 0, 0, so all we are going to do with this K value is take this value and apply it to every single one of these XY coordinate points. We're going to take it and multiply it by each and every XY value from the original points to get our new ones. Therefore, A, which was -2, 3, will become A prime, -4, 6. B prime will turn into 2, 2. C prime will turn into 10, 8. And if I plot those points accurately, -4, 6, 2, 2, and 10, 8 for my B prime, or take that back, C prime, B prime, and A prime values, you should see that we get an object that first of all looks bigger, but has the same shape. Okay, if you look at this ABC, the original here, and you compare it to the A prime, B prime, C prime, it does look the same. We're just looking at a larger version. And if you wanted to go on to really prove that, what we could do is use Pythagorean theorem here between A and B. Just count the blocks and do our Pythagorean theorem to find the distance here between A, B, and then also point out that A prime to B prime is that same value, just doubled, because our scale factor is K equal to 2. But in short, whatever the scale factor is, you're going to take that value and multiply it by the X and the Y to come up with your new point. The X and the Y for your new B point, X and Y for however many points that you have. That K equal to 2, as you can see, or as the number would have originally indicated, is an enlargement. Let's try this final problem. What happens if we were to shrink it? Same object, we'll go with K equal to 1/2. Again, you've got your original points, A and B, B to C. So there's our triangle ABC. You take each one of these values here and just multiply them by 1 half. So the new a prime is negative 1 comma 3 over 2, or 1.5. B prime, 1 half over 1 half. C prime, 5 over 2 over 2. I would say at this point, make a decision. Either go with fractions or go with decimals. Just stay consistent. If you go with 1.5 here, remain with 0.5, 0.5, and 2.5. If you go with the fraction here, go with the fraction throughout. This will require us to estimate to the best of our ability where these points are going to be located, but nonetheless, negative 1 comma 3 over 2, I go left 1 up 1.5. So for that reason, some of you may prefer to go with the decimals. 0.5, 0.5 is your b prime. 5 over 2, which is 2.5, up 2 is c prime. Connect. You see we have the same diagram we had before, just a miniature version. We just have a miniature version between those two. And just to check, between A and C, if you take a look at that, we are going, at that point, up a half of unit. And from A to C prime, we're going up 1/2 unit over 1, 2, 3.5 this way. From A to C, notice how we're going up 1 full unit over 1, 2, 3, 4, 5, 6, 7. So you can see the distance there has doubled. So again, from A prime to C prime, we go up 1/2 unit, right 3.5 units. On the original A to C, we're going up 1 full unit, which is double, and 7 to the right, which is double. That means the original larger than the new one. That's why we have a scale factor of 1/2. Therefore, we have a reduction. This is dilations, and now at this point when we finish dilations, the next thing we'll do, which will be done in a group setting, is putting all of these transformations together and doing what's called a compositive transformation, where you may be dilating an object and then shifting it or rotating it, as you might do with some objects as described with the pictures earlier, i.e. SpongeBob and the Fast and Furious.